Okay, this is friction and angles. And let me increase the volume here. Um, yeah, so we have a block, mass M is 12 kilograms, and we are pushing down on it, downward and to the right with a force F1, which is 60 newtons. And of course, the block will slide in this direction. There is friction, there is kinetic friction, mu sub k. The coefficient of kinetic friction is 0.3. And the angle at which we're pushing is 27 degrees. Okay, so first we will draw a free body diagram for the block. You can just draw this. There is gravitational force mg. There is a normal force Fn. And there is a force F1. Try that again. There's a force F1 right here. And don't forget, because we get used to doing problems without friction, that there is friction here. It will oppose the direction of slipping, so it's slipping off to the right. And so we'll put some friction there. Now, of course, getting started here, we need to take F1 and we need to make components with F1. So we're going to draw this again. And here is mg, ff, fn. And the components of F1, notice how it's going down and to the right, so we have one going down. And we have one going to the right. The vertical one is F1 sine theta. And the one horizontal is F1 cosine theta. Cool. The one that's worth credit, of course, is the free body diagram, which is the top one. These are all the real forces that are on the box or block. And but this one we will use. And so part B, what is the acceleration of the block? And recall that we said that the block is accelerating to the right. And so we want F1 cosine theta and we want the friction force. Let's do this. Okay, we're using this dimension here. There is acceleration. This is F1 cosine theta minus the friction force. The friction force is a kinetic friction. That's mu sub k Fn. And Fn, what is Fn equal to? Fn is not equal to just mg. Fn is equal to F1 sine theta plus mg. Whoops. Minus. Okay. Equals ma. Cool. You could distribute this. I think I'm just going to substitute numbers in here. So we have 60 cosine of 27 degrees minus mu sub k is 0.3. 60 sine 27 degrees plus mg is 120. equals 12a. And we just type this all in the calculator. 60 cosine 27. .29 equals 12a. We'll divide by 12. Oops. I am getting 0.77 meters per second squared for the acceleration. So don't forget when you are doing these problems to label your answers. So part A is right here, part B is right here. Box in your answer, units, give units. Cool, I think this one's done. Let's try another one. This one is without numbers. We're pulling a block with a rope tension force, and it is going upslope. There is friction. Given the mass, the coefficient of kinetic friction, and the angle theta, let's find the tension required to pull the block upslope at constant velocity. First thing I'll do is draw a free body diagram. Let's try that again. Can I draw a dotted line? I know how to do it. Sorry about that. Dashed line. Cool. All right. Here's the block. And the free body diagram will include the gravitational force, mg. There will be a tension force here, Ft. There is a normal force, Fn. And it is sliding up slope, so it is slipping up. We want to put a friction force here. Cool, that is the free body diagram. So sorry about that, the box came out kind of crooked there. That's okay. Now we're going to draw another one, but with the gravitational force broken into components. But why is that, right? So, sorry, let me just organize this a little bit. So, it's sliding, in the direction of the slope of the inclined plane. So Ft and Ff are in great directions that we can, use Newton's second law with. Fn is perpendicular to that, and I didn't draw it very well, but Fn is perpendicular, so that's great. Mg is the only one that is neither is neither along the slope or perpendicular to the slope, and so we want to turn Mg into components. With one component, actually let's use a solid line. With one component in this dimension, and in one component along this dimension here. So I'll draw that here. This one is mg cosine theta, and this one right here is mg sine theta, which I have run out of space to write. mg sine theta. Now let's do part A. We want to find the tension, so we're going to use Newton's second law. We want to use this dimension. So Ft, oh, and by the way, if we're pulling the block upslope at constant velocity, there is no acceleration. So equals 0. We're going to take Ft minus the friction force, also minus mg sine theta. Remember that sine slides, in this case for inclined planes. So Ft equals Ff plus mg sine theta. And so now we have an expression for Ft, for the tension force, but we want it in terms of mass, mu sub k, and theta. So it looks like theta, mass, and g. G is a fundamental constant, so we're good with the mg sine theta. The friction force we need to write in terms of m, mu sub k, and theta. So what is the friction force? It is mu sub k times Fn plus, well, that's not Ff, but we have to add the mg sine theta. U sub k is fine, but the normal force we need to write in terms of m, mu sub k, and theta. Well, the normal force, if you look at this diagram here, is equal to mg cosine. There are no accelerations in this direction, in this dimension. So this is mg cosine theta, and we'll bring down the mg sine theta. Cool. This right here is actually perfectly fine. This is good. We have everything in terms of mu sub k, mass, g is a fundamental constant, and theta. So that looks good. You could have also have written it as mg times mu sub k cosine theta plus sine theta. Cool. That looks good to me.